Hi, class. So we're going to start chapter 13 this coming week. And here's another shot of Columbia College campus, and this is called the Oak Pavilion. This is where, this is a sports arena and also has classrooms for PE classes and offices for faculty. This is also where graduation would have been held this spring if we would have had a graduation. So hopefully we will have graduation next spring. So let's get started. So we're going to do chapter 13, which is on chemical equilibrium. So let me share my screen with the PowerPoint. So here's our PowerPoint slide. I want to stop my video, back to the slide. So this looks like it's the end of the slide. So let's start from the beginning. Here we go. Okay, so this chapter is part of a 3-chapter unit on equilibrium. So chapter 13, chapter 14, and chapter 15. And this is an overview of equilibrium and how to do some equilibrium problems. And then in chapter 14, we'll be focusing on acid-base equilibrium. And then in chapter 15 on salts that are partially soluble. So equilibrium of salts in solution, in aqueous solution. So we'll be doing this for the next 3 weeks, studying equilibrium. So a few of the learning objectives for chapter 13 is to understand the concept of dynamic equilibrium and how it relates to chemical kinetics. So we'll be talking a little bit about or referring back to chapter 12. And this first objective we'll cover in this lecture today on chapter 13.1. Also, we learn what equilibrium constants are, how to write them, and how to use them in calculations. Also, understanding a principle called the Chatelier's principle, which is a qualitative way to understand how chemical equilibrium systems will change when they're not in equilibrium. And lastly, in section 13.4, we'll be doing some calculations involving the equilibrium expressions. Let's go to chapter 13.1 right now. And there's no worksheet associated with this chapter. This is an introduction to what dynamic equilibrium is. And after this, when we get to 13.2, we will be doing a couple of worksheets. The second objective here, this actually goes with 13.2, learn what the equilibrium constant is and how it is determined, how it changes with conditions or some chemical equation. So that's a objective for 13.2. So here's a little illustration of what equilibrium is. This is not chemical equilibrium, but there's a state of equilibrium that is shown in this little animation here of 2 jugglers throwing these stars back and forth. So the juggler on the right has to be turning these stars over as fast as the juggler on the left to be able to maintain this state of constant juggling. And this would be when a system is in chemical equilibrium, we call it a steady state. And it's steady because the concentrations of the reactants and the products are not changing. Well, these 2 jugglers have to be in a steady state. They have to be juggling at the same rate to be able to maintain this steady state. So enough of that. Let's go back to our slideshow. Another steady state that occurs chemically is when you put a liquid in a closed container and you establish a vapor pressure. Well, the vapor pressure is caused by the pressure of the gas molecules inside that container. And for that to occur, it means you have to have an equilibrium between the vapor phase and the condensed phase. And so the evaporation has to be occurring as quickly as condensation. And initially, when you close a container, the pressure is atmospheric pressure. And then as the vapor becomes in equilibrium with the liquid, you'll establish an additional pressure caused by the pressure of that gas in the container. And then that pressure doesn't change, it reaches an equilibrium. So the amount of gas molecules reaches equilibrium with the liquid molecules. So we could state that the rate of vaporization is equal to the rate of condensation and dynamic equilibrium is reached. So what does a chemical equilibrium system look like? Well, this is one. This is a dinitrogen tetroxide in equilibrium with nitrogen dioxide. And when we write an equilibrium expression using our chemical formulas, we would put an arrow in between the two formulas. So we have a forward arrow indicating a change in the right direction to the right, and a reverse arrow indicating the reverse change from the right to the left. And so whenever you see a chemical reaction written this way, it means this is a dynamic equilibrium. And previously, we just wrote reactions with the arrow going to the right. And that would indicate that it's almost a complete reaction, that the products or the reactants turn entirely into products, and that the reverse doesn't occur to any appreciable extent. In the dynamic equilibrium, we would write the arrows this way to indicate that we're going to use an equilibrium expression to calculate the different concentrations that might occur in this chemical system. So what would that look like if we started with only N2O4 and then over a period of time watch the formation of NO2? Well, that would look something like this, an equilibrium expression. If we start with 0.04 moles per liter of N2O4, it's going to decrease as the formation of NO2 occurs. And pretty soon the concentration of N2O4 stops changing and the formation of NO2 stops occurring until they both reach a concentration that doesn't change. Well, when this happens, the system is at equilibrium. So one thing you'll notice I'd like you to point out is that the change in concentration of N2O4 is about half the change in the formation of the concentration of NO2. So that matches the stoichiometry of this equilibrium expression. And you get 2 molecules of NO2 for every molecule of N2O4 that disappears. Now, let's look at another situation. Let's look at the situation where we start with NO2. That would be the reverse reaction. So it shows the reverse arrow here, NO2 going to N2O4. And remember on the left side, when we started with N2O4, we started with 0.04 moles per liter. Well, the stoichiometry says that there's twice as many NO2 as N2O4. So if we start with 0.08 moles per liter of NO2, if this reaction occurs to the same extent, we would say if it went to 100% of N2O4, we'd end up with 0.04 N2O4, which is the same as shown on the left side. So let's see what happens. So we start with NO2, it disappears rapidly. And it goes down until it reaches a steady state of about a little over 0.01 moles per liter. And N2O4 forms until it reaches a concentration of about 0.035. Well, notice the concentrations on the left side at equilibrium and on the right side are the same. They reach the same state of concentrations. Now, when this happens, it means that since the concentrations aren't changing, this chemical reaction is still occurring, both forwards and backwards. But because the concentrations aren't changing, it means the rate of the forward reaction is equal to the rate of the reverse reaction. And even though the concentrations are different, the rates are the same. Remember initially, or back in chapter 12, we said that the rate has to do with the concentration of the substance that's undergoing the change. The greater the concentration of the substance, the faster the rate of change. And that's what you see here, is that the when we start with NO2, boy, it disappears pretty rapidly. But then the disappearance slows down as the concentration decreases. And the same with N2O4. We have a rapid formation of N2O4, and then it slows down until both rates slow down to the same extent so that the forward reaction and the reverse reaction are equal. And then the concentrations don't change anymore. This graph here shows the rate of change. And if we start with N2O4, and I think these represent, this is the reaction rate, the change. Remember, the reaction rate is the change over time. This isn't the change in concentration, it's the reaction rate. And so initially, because there's no, go back, because there's no NO2, it changes, the reaction rate keeps increasing very, very rapidly. So as the concentration of NO2 increases, the rate of change increases. Makes sense. As the concentration of NO2 increases, the rate of change increases. As the concentration of N2O4 decreases, remember we started with N2O4, but it's disappearing, the rate decreases until the rate of disappearance of N2O4 is equal to the rate of disappearance, or the rate of formation or disappearance of NO2. So this is the reverse reaction. So the rate of the reverse reaction is shown here. As NO2 is formed, the rate of the reverse reaction increases, true, until it just becomes steady. And the rate of the reverse is equal to the rate of the forward. And when that happens, let me go backwards. Oops. When that happens, the concentrations don't change anymore. So in summary, when a reaction reaches equilibrium, no further change in concentration takes place. So the concentration of the reactants and the product stays constant. And why that occurs is because the rate of the forward reaction is equal to the rate of the reverse reaction. So that's the end of this short lecture on dynamic equilibrium and why it occurs. And the next lecture will be in chapter 13.2, which talks about the quantitative aspects of dynamic equilibrium. So I'll leave you with that, and next time, the next lecture will be in chapter 13.2. Goodbye.